Hi students, all of you welcome. Welcome to Suneel Engineering Academy. I am Sunil Kumar Bandar. Students, in this transformers, recently we have completed two sessions. It is the third one, useful for all your competitive examination. Okay, let me check up to which we have completed. So basics we have completed, constructional details, transformer windings and types, core type and shell type completed. Okay, and different parts of the transformer and stacking factor. Up to this we have completed. Okay, now we are going to discuss the characteristics of ideal transformer. After that we go with the EMF equation. Okay, so characteristics of ideal transformer, very important guys. So in most of the exams they have given one question on this characteristics of ideal transformer. As you know very well, what is meant by ideal? Ideal is perfect. Okay, ideal is nothing but you can say perfect without any flaws, without any negatives. Okay, only positives. Okay, so what are the ideal, perfect characteristics of transformer? First one, whatever the power you have sent at the receiving end, also you have to get the same power. Correct? Okay, without changing the frequency. When it will be possible? Whenever the losses are less. Losses almost zero means then whatever the output power, whatever the input power, that is will be output power. Correct? So must be winding resistances are less. Okay, so the first point you can say winding resistances are zero. Winding resistances are zero. Okay, so if the winding resistances are zero, zero losses. So that means copper losses are zero. Okay, and leakage flux must be zero. So magnetic leakage flux is zero. When magnetic flux will be, leakage flux will be zero, whenever we have that means perfect coupling, whenever we have perfect magnetic coupling, that means K must be equal to 1, then leakage flux will be 0. And let us take whatever the flux produced in the primary winding, it must be linked to the secondary winding. Okay, that means it has to be transferred without reluctance, okay, to the second part. So that means you can say permeability of transformer core must be very high or infinity. Permeability, it is the ability to permeate the flux of transformer core is infinite. Then only all the flux will be flow through the core. Okay, and iron losses considered to be zero. Iron losses are zero, assumed to be zero in case of ideal transfer. And magnetization curve must be linear without saturation. Magnetization curve, generally it is the it goes to the saturation, but ideal case it must be linear. Magnetization curve of transformer core is linear. We have to get the transformer and characteristics are like this. Okay, so linear characteristics, but in general case it will be like this. Okay, saturation. Okay, so it must be linear in the nature. So all these are important characteristics of the ideal transformer. Ideal transformer. Here the next one, EMF equation. EMF equation. You know very well about the EMF equation of a transformer. EMF. Let us take EMF is equal to 4.44 pi m f n. Okay, so if you go with the primary turns, that will be a primary EMF. Okay, primary EMF. If you go with the secondary turns, that will be a secondary EMF. Pi m f into. Okay, and here pi m is nothing but A into B. A into B. Okay, here let us take a net cross section area generally, maximum flux density. We know the flux density is equal to flux by unit area, correct? You know very well. And here from that pi is equal to AB. BA or AB. So AB is easy to remember. A, B, C, D, E, F like that. Okay. So pi is equal to A into B. So here we can consider E2 is equal to 4.44 in the place of pi A, B, F, N. Okay. So if you take the ratios of these two, E2 by E1, E2 by E1. Okay. E2 by E1. That will be N2 by N1. Correct. So if you take the flux is constant, frequency is constant, 4.44 is a constant, E2 by E1 is equal to N2 by N1 you will get. Okay, N2 by N1 you will get. So we know very well in the transformer, power is a constant, then EMF into current is a constant. If the EMF is more, current is less. So inversely proportional. So then E2 by E1 is nothing but I1 by I2 now. I1 by I2. And we know very well current is always with respect to area of the conductor. If whenever the area is more, it has transferred the more current. Okay, so that means I1 by I2 is equal to cross section area A1 by A2. A1 by A2. So this is the relation. Very, very important, guys. Very, very important relation. Very, very important relation. Okay. And here, very important point here, E1 comma E2 are induced EMFs of transformer in which form? RMS form. RMS form. That is the important bit for A examinations. Okay. And N1, N2 are primary and secondary terms. N1 comma N2 are primary and secondary terms. Okay, primary and secondary terms. Here we have some observations on EMF equation. That is the very important, guys. Observations of EMF equation. Observations of EMF equation. Here you can learn a very important points. Okay, exam purpose points. Okay, here we know E2 by E1 is equal to N2 by N1. That is generally you can say K. K is nothing but transformation ratio. Transformation ratio. Okay. Transformation ratio. And so K is equal to N2 by N1. That is equal to 1 by N1 by N2. Correct? 1 by N1 by N2. 1 by N1 by N2 is considered as a turns ratio. Turns ratio. A. Okay, from this one, we can say K is equal to 1 by A. Okay, that means A is equal to N1 by N2. A is equal to N1 by N2. Okay. So this is the very important thing. Okay. Most of the students having confusion. K is equal to N2 by N1. A is equal to N1 by N2. A is the turns ratio. K is the transformation ratio. It is the turns ratio. Okay. Second observation. Second observation. EMF E is equal to 4.44 pi Fn. So I am substituting here pi is equal to A into B. Okay. E is equal to 4.44 ABFN. Okay. B is nothing but B max. A is nothing but net cross section area. Okay. Net cross section area. Here, in that case, once the transformer is manufactured, once the transformer is the manufactured, then number of turns is constant, cross section area is a constant. Okay, is a constant. Then 4.44 is also constant. Then EMF is proportional to remaining variable quantities, maybe flux density and frequency. Okay, so we can operate this whatever the flux and whatever the frequency. From this one, we can get V max is proportional to E by F. V max is proportional to E by F. So flux density depend upon EMF by frequency. That means voltage by frequency. Voltage by frequency. Okay. So B max is proportional to voltage by frequency. If voltage and frequency are constant, then B max is a constant. So for example, if B max is equal to constant, if you want to get constant flux density, then what we have to do? We have to give V by F constant. V by F is constant. Very important relation. If the B max is constant, that means V by F is the constant. Okay. V by F is constant in the sense V1 by F1 is equal to V2 by F2, or V1 by F1 is V2 by V2 by F2 is equal to V1 by F1, whatever it may be. Okay. So based on this, a lot of questions are framed. Like, if a transformer having, example question, if a transformer having 240 volts, 60 hertz is operated, 240 volts and 60 hertz, then its B max is 1.2 Tesla. If you operate the same transformer, if you operate the same transformer for 160 volts, and the frequency you don't know, and you need to get the same B max. Okay, so in the first case, the transformer is operated with voltage and frequency, then you will get B max 1.2 Tesla. If you reduce the voltage 240 to 160, still you want to get the same B max, then what is your frequency? So here in the solution, how you can do this solution? B max is a constant, correct? If the B max is constant, what is the relation you know? B max is proportional to V by F. So V by F is constant. V by F is constant. Okay. So that means if you reduce the voltage, frequency also reduces. So if you reduce the voltage 240 to 160, you need to reduce the frequency from 60 to 40. 60 to 40 hertz, then you will get the same now, correct or not? So if you reduce the voltage as half, frequency also half. Half means 120, but it is not 120, more than 120. So if the half is 30, so it is more than 30, 40. Okay, still you want, you can calculate like your conventional formula. V1 by F1 is equal to V2 by F2. From this, V1 is 240, F1 is 60, V2 is your 160, F2 is you need to find out. Okay, so 44s, 46, 6 ones, 6 tens. From this, F2 is equal to 40. So like that also you can calculate in your traditional way, or otherwise you can go with logic. V by F is constant means if you reduce the voltage in the same proportionality, frequency also reduces. Okay, so like that you can calculate the problems in a easy manner. Okay, in a easy manner. All of you clear? And some more observations let us take from that. Some more observation. B max is proportional to V by F. Okay, V by F. If voltage is equal to constant and frequency is reduces, then what will happen? Okay, if the voltage is constant and frequency is reduces, if the frequency is reduces, B max is more. B max increases, correct? Why? Because it is proportional to V by F. If the frequency is reduces, B max is more. Okay, if the B max is more, that means flux requirement is more. If you want to get more flux requirement is more. If you want to get more flux, your magnetizing current must be more. Your magnetization current must be more. So magnetizing current increases. Okay, if you keep your voltage as constant and if you increase the frequency, then what is the consequences? Reverse. V by F, frequency increases, B max is less, flux requirement is less, so magnetizing current requirement is less. Magnetizing current requirement is less. Okay, all of you clear? And the next observation, EMF E is equal to 4.44 pi EFN. I am substituting in the place of pi as AB, 4.44 pi as A B F N. Okay, A F A N B, sorry, A N B M F N. Okay, now in this case, if flux requirement is constant, then AB is equal to constant, correct? AB is equal to constant. Okay, if the flux requirement is constant, AB is equal to constant. In that case, EMF is proportional to frequency. EMF is proportional to frequency. If the frequency is more, then the EMF will be more. EMF will be more. And another case, E is equal to 4.44 AN BM FN. Okay, and if you want make B max as constant, N is a constant. Okay, 4.44 is always constant na? So EMF is proportional to AN BM. If you want constant EMF, if you want to AN F, B max also we have taken constant na? So AN F. Okay, so if you want to make E as constant, okay, if you increase the frequency, then cross section area will be reduced. That means if you go with less cross section area also, you will get the same EMF. Okay, so E is proportional to AN into F. If we increase frequency, area requirement is less. Okay, area requirement is less. If the area requirement is less, then specific weight of the transformer is less. Specific VIGHT weight of transformer is less. Okay, specific weight of the transformer is less. All of you clear? So that means for same EMF, same EMF means same kVA. For same EMF, that is same kVA, frequency is more, then area of the cross section is less, then size of transformer is less, portable. It will becomes portable. As the high frequency, the size of the transformer is less. Okay, the size of the transformer is less. For example, if we have three transformers, transformer A is a 40 kVA transformer. It is operated at 50 hertz. Option B, same 40 kVA transformer operated at 60 hertz. Okay, same transformer 40 kVA with 120 hertz, which is the smallest. So it is considered as the smallest transformer. Okay, size is small. Why? Because as frequency is more, the area requirement is less. Okay, then it will become the smallest transformer. Okay, so we have the questions in the MCQ session. Okay, so this concept will be very much useful. Very much useful. Okay, all of you clear? Okay, yes. Okay, students, we will discuss the remaining questions in the next session. In the next session, we will take the next points, that is about operation of transformer with iron losses. Okay, I naught, I mu, IW, and the differences between those, and the equivalent circuits, lagging and leading power factors, and we will discuss all those in the next session. Okay, if you want download the electrical engineering PDF for your RRB, JE, or SSC, JE, or whatever it may be, you can download, you can visit suneelengineeringacademy.com and go for the process. After the full process, click on my account and downloads, then you will get the PDF. Okay, so if you visit the site, in that site you have the link for the video how to download. Okay, so if you go with the website, the first video is there how to download the PDF. Watch that 1 minute video, then you will get the idea how to download the PDF. Okay, okay students, all of you, thank you so much for watching. Take care. Bye guys.